Welcome the students of SC Civil for the subject Concrete Technology, Unit number 1. The title is Introduction to Concrete and Ingredients of Concrete. So here we will use the reference books, the Concrete Technology Theory and Practice by M.S. Shetty. Second, Concrete Technology Theory and Practice by M.L. Gambhir, and Properties of Concrete by Adam Neville. So first we will see the course objectives. First course objective is to know the properties of various ingredients of concrete and concept of mixed design. Second course objective, to learn the behavior and properties of concrete in fresh and hardened state. Third, to understand the special concrete and their applications. Fourth course objective is to understand the durability aspects and preventive measures to enhance the life of the concrete. Then we will see the course outcomes. First course outcome is students will be able to select the various ingredients of concrete and its suitable proportion to achieve desired strength. Second course outcome is to able to check the properties of concrete in fresh and hardened state. Third course outcome is to get acquainted to concreting equipments, techniques and different types of special concrete. Fourth course outcome is to able to predict deterioration in concrete and get acquainted to various repairing methods and techniques. So unit number 1, Introduction to Concrete and Ingredients of Concrete. It includes part A and part B. Part A includes cement and aggregate, which includes manufacture, chemical composition, hydration, physical and mechanical properties, classification, types and application of cement, test on cement, classification of aggregate, physical and mechanical properties of aggregate, deleterious materials in aggregate, alkali aggregate reaction, fineness and gradation of aggregates using sieve analysis, test on aggregates. The B part includes, second part in unit number 1, water and admixtures, quality of water for use in concrete, role of admixture, classification and types of admixtures like accelerators, retarders, plasticizers, superplasticizers, mineral admixtures such as fly ash, silica fume, ground granulated blast furnace slag. So here we will see part A, cement and aggregate. In that we will see first part the manufacture of the cement, second is the chemical composition, third hydration of the cement, fourth physical properties, fifth mechanical properties and sixth classification of the cement. So Joseph Aspen took the patent, that is the British patent BP 5022, entitled An Improvement in the Mode of Producing an Artificial Stone, in which he coined the term Portland cement by the analogy with the Portland stone of the Portland cement on 21st October 1824. The fancy name of the Portland was given owing to the resemblance of this hardened cement to the natural stone occurring at the Portland in the England. So first we will see the cement, the manufacturing of the cement. The raw materials required for the manufacture of the Portland cements are calcareous materials and areous materials. Calcareous materials containing the calcium carbonate or lime, such as limestone or chalk, and areous materials containing alumina, such as shale or clay. Prior to the manufacture of Portland cement in India, it was imported from UK, that is London, England, and only a few reinforced concrete structures were built with imported cement. A three-storied structure built at Baikala, Mumbai is one of the oldest RCC structure using Portland cement in India. A concrete masonry building on Mount Road at Chennai, it was built in 1903. The Harki-Pahadi Bridge at Haridwar, it was built in 1908, and the Cotton Depot in Mumbai, then one of the largest of its kind in the world in 1922, are some of the oldest concrete structures in India. In India, Portland cement was first manufactured in 1904 near Chennai by the South India Industrial Limited, but this venture was failed. Between 1912 and 1913, the Indian Cement Company Limited was established at Porbandar, that is in Gujarat, and by 1914, this company was able to deliver about 1,000 tons of Portland cement. By 1980, 3 factories were established in India. Together, they were able to produce about 850,000 tons of cement per year. So first we will see the manufacture of this cement. In India, so here we can see the manufacturing can be done by the 2 methods. One is by dry process, another is the wet process. So here we can see the dry process. In the dry process, the limestone is first crushed and it is mixed with the clay or shell. The temperature is about 1200 degrees Celsius, because as it is the dry process, so the ingredients are not in the wet condition, so temperature is comparatively less compared to wet process. The fused mass turns into the nodular form of size 20 mm known as clinker. By moderate cooling from about 1200 degrees Celsius, the clinker is brought to about 500 degrees Celsius in about 15 minutes. And from 500 degrees Celsius temperature is brought down to normal atmospheric temperature in about 10 minutes. So like this the temperature is varied. The cooled clinker is then ground into a ball mill with the addition of 3 to 5% of gypsum in order to prevent the flash setting of the cement. So as like in the POP, plaster of Paris, as we add the water in that, it's set fastly. So same, it should not happen. So the gypsum is added in the cement. So here we can see the flow diagram for the cement manufacturing by dry process. The another type of the process is the wet process. In the wet process, the limestone is first crushed and it is mixed with the clay or shell and ground to a fine consistency of slurry with 35% to 50% addition of water. So here the water is added and so it is called as the wet process. The temperature here is 1500 degrees Celsius. In dry process it was 1200 degrees Celsius. So here the temperature is 1500 degrees Celsius because it is in wet condition. About 20 to 30% of the materials get fused. Lime, silica and alumina get recombined. The fused mass turns into nodular form of size 20 mm known as clinker. The cooled clinker is then ground in a ball mill with the addition of 3% to 5% of gypsum in order to prevent the flash setting of the cement. So here we can see the wet process in the chart. So we have seen the manufacturing of the cement. Now secondly we will see chemical composition of the cement. So here table 1 shows approximate oxide composition limits of the ordinary Portland cement. So here oxide name is given, oxide is there and percentage content. So oxide name is calcium oxide, it's designated as CaO and 60 to 67% is the content in the cement. Next is the silicon dioxide, it is designated as SiO2. Normally 17 to 25% content is there in the cement. Next is the aluminum oxide, Al2O3, 3 to 8% is the content in the cement. Next is the iron oxide, Fe2O3, normally it is 0.5 to 6% in the cement. Next is the magnesium oxide, MgO, normally it is 0.1 to 4%. Next is the potassium oxide and sodium oxide. Potassium oxide is K2O and sodium oxide is Na2O. Normally it is called as the alkalis. It is 0.4 to 1.3% in the cement. Next is the sulfur trioxide, that is SO3, 1.3 to 3%. So we have seen the chemical composition of the cement. Then the table 2, it shows the Robert H. Box's major compounds. They are also called as the Box compound. The Box compounds are 4: tricalcium silicate, dicalcium silicate, tricalcium aluminate and tetracalcium aluminate ferrite. Normally the formula for the tricalcium silicate is 3CaOSiO2. It is abbreviated as C3S. Its percentage is normally 54.1%. Second Box compound is dicalcium silicate. Its formula is 2CaOSiO2. It abbreviated as C2S. The percentage content is 16.2. Third Box compound, major Box compound is tricalcium aluminate. Its formula is 3CaOAl2O3, that is abbreviated as C3A. Its content is 10.8%. And fourth major Box compound is tetracalcium aluminate ferrite. It is 4CaOAl2O3 Fe2O3. It's abbreviated as C4AF. The percentage content is 9.1%. So here table number 3, it shows oxide composition of a typical Portland cement and the corresponding calculated compound composition. So here the oxides are there and the Box compounds. So the oxide is CaO, normally it is 63%. The Box compound tricalcium silicate C3S, it is 54.1%. Then oxide is SiO2, silica, its percentage is 20%. Dicalcium silicate C2S, that is the Box compound, its percentage content is 16.6%. Then the alumina Al2O3, its percentage is 6. Tricalcium aluminate, Box compound C3A, its percentage content is 10.8. Iron oxide Fe2O3, its percentage is 3. Tetracalcium aluminate ferrite, it is 9.4. Then MgO magnesium oxide 1.5. Then alkalis, they are called as the minor compounds by the Box compound, K2O and Na2O, it's 1%, and sulfur trioxide, it is 2%. So here the figure 3 shows the schematic representation of various compounds in the clinker. So here the figure is of clinker. So here we can see the blue color is C2S, then this reddish color the C3S, and in between this color C3A plus C4AF, it is shown. Then the Box major compounds are tricalcium silicate, it is C3S, dicalcium silicate C2S, tricalcium aluminate C3A, and tetracalcium aluminate ferrite, that is C4AF. So these are the 4 major Box compound. Similarly, Tribun also called the 4 kinds of crystals as like alite, belite, silite and phyllite respectively to the Box major compounds. The tricalcium silicate, that is C3S, and dicalcium silicate, C2S, are the two most important compounds responsible for strength. Together they constitute normally 70% to 80% of the cement. The average tricalcium silicate, that is C3S, contained in modern cement is about 45%, and that of the dicalcium silicate, that is C2S, is about 25%. The sum of the contents of tricalcium aluminate, that is C3A, and tetracalcium aluminate ferrite, C4AF, has decreased slightly in modern cements. To manufacture a cement of stipulated compound composition, it becomes absolutely necessary to closely control the oxide composition of the raw materials. An increase in the limestone content beyond a certain value makes it difficult to combine with other compounds, and free lime will exist in the clinker, which causes unsoundness in the cement. An increase in silica content at the expense of content of alumina and ferric oxide will make the cement difficult to fuse and to form a clinkers. Cements with a high total alumina and high ferric oxide content is favorable to the production of high early strength in the cement. This is perhaps due to the influence of these oxides for the complete combining of the entire quantity of lime present to form the tricalcium silicate, that is C3S. So we have seen the second point, that is chemical composition. Now we will see the third point, that is the hydration of the cement. So the hydration of the cement is it is an anhydrous cement, does not bind fine and coarse aggregate. So here if we take the cement and fine aggregate and coarse aggregate, and if we mix it in dry condition, that is anhydrous cement, they will not get bind together. So for the binding purpose, water has to be added. It acquires adhesive property only when mixed with water. The chemical reaction that takes place between the cement and the water is referred as the hydration of the cement. The chemistry of concrete is essentially the chemistry of the reaction between the cement and the water. On account of hydration, certain products are formed. These products are important because they have cementing or adhesive value. The quality, the quantity, the continuity, the stability, and the rate of formation of the hydration products are very much important. So here we can see in the figure heat liberation from a setting of the cement. So on horizontal axis the time is given in hours, and in vertical axis the rate of liberation, calories per gram per hour, it is given. So as soon as we add the water in the cement, the rate of liberation of the oxygen is very high, and then gradually it will start decreasing, and again it will get increase, and gradually it will get decrease. So like this, as per the time and the rate of liberation is shown in this graph. So here the hydration of the cement, the reaction of the cement with the water is exothermic. So here the oxygen is get liberated. The reaction liberates a considerable quantity of the heat. The liberation of heat is called as the heat of hydration. On mixing cement with water, a rapid heat evaluation lasting a few minutes occur. The heat evaluation is probably due to the reaction of solution of aluminate and sulfates, that is exceeding peak A value. So previously we can see this A value is there because of the solution of aluminates and the sulfates. This initial heat evaluation sees quickly when the solubility of aluminate is depressed by gypsum descending peak A. So here we can say whatever the descending is there, this is because of the addition of the gypsum. Next, heat evaluation is on account of formation of intrusion and also may be due to the reaction of tricalcium silicate, that is C3S, ascending peak B. So here this is due to the attringent, that is C3S. So here hydration of the cement, it can be calculated by the formula H is equal to A plus B plus C plus D. So here small a capital A plus small b capital B plus small c capital C plus small d capital D. So summation of all A, B, C, D is done, where capital H represents the heat of hydration. Then the capital A, B, C, D, these are the percentage contents of C3S, C2S, C3A and C4F. These are the four major box compound. The percentage content is given in capital A, B, C, D. And small a, b, c, d, these are the coefficient representing the contribution of 1% of the corresponding compound to the heat of hydration. They are small a, b, c, d. So addition of all this, that is small a multiplied by capital A plus small b multiplied by capital B plus small c multiplied by capital C plus small d multiplied by capital D. Normal cement generally produces 89 to 90 calories per gram in 7 days and 90 to 100 calories per gram in 28 days. The calcium silicate hydrates, during the course of reaction of tricalcium silicate, that is C3S, and dicalcium silicate, that is C2S, with water, calcium silicate hydrate, that is CSH, it is abbreviated, and calcium hydroxide, that is CaOH2, are formed. Calcium silicate hydrates, that is CSH, are the most important products in the cement hydration. It is essential that determines the good properties of the concrete. Tricalcium silicate, that is C3S, readily reacts with water and produces more heat of hydration. So it is responsible for early strength of concrete. Then dicalcium silicate, that is C2S, hydrates rather slowly. It is responsible for the later strength of the concrete. It produces less heat of hydration. Normally, if we want early strength, then maximum quantity of C3S can be used, and if we want later strength, then maximum quantity of C2S can be added. The calcium silicate hydrate, that is CHH, formed is rather dense and its specific surface is higher. During the course of reaction of tricalcium silicate, that is C3S, and dicalcium silicate, C2S, with water, the calcium silicate hydrates, that is abbreviated as CSH, and calcium hydroxide, CaOH2, are formed. The lack of durability of concrete is on account of the presence of calcium hydroxide. The calcium hydroxide also reacts with sulfates present in soils or water to form calcium sulfate, which rather reacts with tricalcium silicate, that is C3A, and causes deterioration to the concrete. This is also known as the sulfate attack. The use of blending materials such as fly ash, silica fume and such other pozzolanic materials are the steps to overcome the bad effect of CaOS2, that is calcium hydroxide, in the concrete. So here in this figure we can see development of the strength of pure compounds. So in the horizontal axis the age is given in days and in vertical axis compressive strength is given in megapascal or Newton per millimeter square. So here the four major box compounds are shown: C3S, C2S, C3A and C4AF. So 7 days, 28 days, 90 days, 180 days, 360 days. Similarly, the compressive strength is also shown. So here the C3S is giving early strength, C2S comparatively low. Like this it is shown. So now we will see the water requirement for the hydration. It has been brought out earlier that tricalcium silicate, that is C3S, requires 24% of water by weight of this cement, and dicalcium silicate, that is C2S, requires 21% of water by the weight of the cement. It has been also been estimated that an average of 23%, that is 24 plus 21 upon 2. The average it will come 23% of water by weight of the cement is required for the chemical reaction with Portland cement compounds. This 23% of water chemically combines with cement and therefore it is called as the bound water. Once again I am repeating, this 23% of water by the weight of the cement chemically combines with water with cement and therefore it is called as the bound water. A certain quantity of water is embedded within the gel pores. This water is known as the gel water. It can be said that the bound water and gel water are complementary to each other. If the quantity of water is inadequate to fill up the gel pores, the formation of gel itself will stop, and if the formation of gel stops, there is no question of gel pores being present. It has been further estimated that about 15% by the weight of the cement is required to fill up the gel pores. Therefore, the total of 38%, that is 23% plus 15%, that will give 38% of water by the weight of the cement is required for the complete chemical reaction and to occupy the space within the gel pores. So this 23, it is here the bound water. This 23% of water chemically combines with cement and therefore it is called as bound water. This 23% and this 15%, it is further estimated that about 15% by the weight of cement is required to fill the gel pores. So the bound water and the gel pores water combined, it will give 38%. So therefore a total of 38% of water by the weight of the cement is required for the complete chemical reaction and to occupy the space within the gel pores. If water equal to 38% by the weight of cement is only used, it can be noticed that the resultant paste will undergo full hydration and no extra water will be required for the formation of undesirable capillary cavities. On the other hand, if more water, that is more than 38% of water is used, then the excess water will cause undesirable capillary cavities in the paste. So we have seen the third part, that is hydration of the cement. Now we will see fourth part, physical properties. So the physical properties of cement, first is fineness. For that we have to refer the Indian Standard Code, that is IS 4031 Part 1. It is published in the year 1996. The title is Methods of Physical Test for Hydraulic Cement. Part 1, it includes determination of fineness by dry sieving. Then second physical property is consistency. It is determined by the IS code, that is IS 4031 Part 4. It is published in the year 1996. The title is Methods of Physical Test for Hydraulic Cement. The part 4 includes determination of consistency of standard cement paste. The third physical property is the setting time. It can be determined by using the IS code 4031 Part 5. It is published in the year 1996. The title is Methods of Physical Test for Hydraulic Cement. The part 5 includes determination of initial and final setting times. The fourth physical property is hydration of the cement. So it can be determined by the Indian Standard Code IS 11262. It is published in the year 1985. The title is Specification for Calorimeter for Determination of Heat of Hydration of Hydraulic Cement. The fifth physical property of the cement is soundness. For that we can refer the Indian Standard Code IS 4031 Part 3. It is published in the year 1988. The title is Methods for Physical Test for Hydraulic Cement. The Part 3 title is Determination of Soundness. The sixth physical property is the strength. For that we can refer IS 4031 Part 6. It is published in the year 1988. The title is Methods of Physical Test for Hydraulic Cement. Part 6, its title is Determination of Compressive Strength of Hydraulic Cement other than masonry cement. The seventh physical property is the specific gravity. It can be determined by using the IS code 4031 Part 11, which is published in the year 1988. Methods of Physical Test for Hydraulic Cement. Part 6 includes determination of density. Eighth property, that is physical property of the cement, is bulk density, and the ninth physical property of the cement is the loss of ignition. So like this we have seen the physical properties of the cement. Now we will see the mechanical properties of the cement. So here the mechanical properties of the cement we can say: first, compressive strength; second, the tensile strength; third, the shear strength; fourth, flexural strength; fifth, modulus of elasticity, or it is also called as Young's modulus. Sixth mechanical property of the cement is Poisson's ratio. Seventh mechanical property of the cement is permeability. Eighth is the coefficient of thermal expansion, and ninth mechanical property of the cement is the drying sinkage. So here we can say the second, tensile strength, the mechanical property of the cement. So tensile strength can be determined by the formula ultimate load upon area. So here the briquette mold is used for the cement. This we can see is the plan, and here we can see as the elevation. This is the standard briquette mold. The tensile strength at the end of the 3 days should not be less than 20 kg per centimeter square or 2 Newton per millimeter square or megapascal, and at the end of the 7 days should not be less than 25 kg per centimeter square or 2.5 Newton per millimeter square or 2.5 megapascal. So, to determine the tensile strength of the cement, we have the apparatus in our lab. So, we have seen the fifth content, the mechanical properties. Now, we will see sixth point, that is the classification of the cement. So, here we can see the classification of the cement as per ASTM, that is American Society for Testing Materials C150. As per that, the cement type is there and the description is given. First, cement type 1, it is normal cement. Cement type 2, moderate sulfate resistance. Cement type 2MH, that is the moderate heat of hydration and moderate sulfate resistance. Then third is the cement type 3, that is high early strength. Next, cement type is 4, low heat hydration, and cement type 5 is the high sulfate resistance. These are the classification of the cement as per ASTM, that is American Society for Testing of Materials. Then next we will see the classification of blended hydraulic cement as per ASTM, that is American Society for Testing of Material C595. First is the type 1L, that is Portland limestone. Second is the type IS, that is 1S, that is Portland slag. Then next type, third type is type 1P, that is Portland pozzolana. Then fourth type is the type 1T, that is ternary blended cement. These are the classification of the blended hydraulic cement as per ASTM, that is American Society for Testing Materials. Next we will see the classification of the cement of performance based cement as per ASTM, that is American Society for Testing Materials by C1157. First type is type GU, that is general use. Second type is type HE, high early strength. Third type is type MS, that is moderate sulfate resistance. Fourth type is type HS, that is high sulfate resistance. Fifth type is type MH, that is moderate heat of hydration. And sixth type is the type LH, that is low heat of hydration. So these are the classification of the cement of performance based cement as per ASTM, that is American Society for Testing Materials. Now we will see the classification of the cement as per European standards, that is EN 197 part 1. So cement type 1 is the Portland cement. Cement type 2, yes, that is Portland slag. Cement type 2C, that is Portland fly ash. Next type of cement is type 2, that is Portland composite. Next type of the cement is 2Z, that is Portland pozzolana. Next type is type 2F, that is Portland filler, that is limestone. Next type of the cement is type 3, that is Portland blast furnace slag. And next classification of the cement, that is type 4, that is fly ash or pozzolana. These are the classification of the cement as per European standard, that is EN 197 part 1. So we have seen the classification of the cement. So these are the YouTube links which are available on the YouTube, that we can see J&K Lakshmi cement manufacturing process. Next is cement manufacturing. Third is the cement production and composition. Next YouTube link, cement production part 1. Next YouTube link, cement production part 2. Next, chemical composition of cement. Next YouTube link, cement hydration of compounds. Next YouTube link, module 1 lecture 5, hydration of the cement. Next YouTube link, module 4 lecture 1, cement hydration. Next YouTube link, cement hydration primer. Next YouTube link, module 4 lecture 2, cement and cementitious materials. So these are the YouTube links that we can see. The overview of process of hydration of cement number 1. Next YouTube link, heat of hydration of cement number 2. Then unit 1 lecture 2, properties of cement, types of cement, concrete technology, third semester. This also YouTube link you can see. Next YouTube link is testing of cement part 1. Next, testing of cement part 2. Next, testing of cement part 3. Next, fineness test of the cement. Next is fineness test of cement by blend air permeability apparatus. Next YouTube link is standard consistency test of cement. Next YouTube link is how to determine the initial and final setting time of the cement test number 2, hydration of cement of Portland cement. Next YouTube link is soundness test by leach address method. Next YouTube link is soundness of cement test. Next YouTube link is how to determine the compressive strength of cement test number 3. Next YouTube link is specific gravity of cement. Next YouTube link, bulk density of cement, LOI, that is loss of ignition. Next YouTube link is tensile strength test of cement. Next YouTube link is how to determine the tensile strength of cement, laboratory test. So here now we can see the test of cement companies in India. First, ACC Cement. Second, Ambuja Cement. Third, Binani Cement. Fourth, India Cement. Fifth, JSW Cement. Sixth, Mycem Cement. Seventh, Ramco Cement. Eighth, Wonder Cement. Ninth, Sri Cement. And 10th, Ultratech Cement. These are the few list of the cement companies in India. So we have seen from unit number 1, introduction to concrete and ingredients of concrete, part A, cement and aggregate. In that we have seen manufacture, cement composition, hydration of the cement, physical properties, mechanical properties, and classification of cement. So unit 1, introduction to concrete and ingredients of concrete. It includes part A and part B. Part A includes cement and aggregate, manufacture, chemical composition, hydration, physical properties, mechanical properties, classification, types and application of cement, test on cement, classification of aggregate, physical and mechanical properties of aggregate, deleterious materials in aggregate, alkali aggregate reaction, fineness and gradation of aggregates using sieve analysis, test on aggregates. The B part, which includes water and admixture, quality of water for use in concrete, role of admixture, classification and types of admixture like accelerators, retarders, plasticizers, super plasticizers, mineral admixtures such as fly ash, silica fume, ground granular, blast furnace slag. Thank you all students.